Welcome everyone to this presentation, which will be about self-learning systems for cyber defense. My name is Kim Hammar, and I'm a PhD student at KTH University in Stockholm, and this is joint work together with Professor Stadler. So self-learning systems for security is about increasing the level of automation in our security systems. And if you look at this from an historical perspective, in the earliest systems, we had basically no automation, very little data, and also very few tools for managing security. Then as time has progressed, we have gotten better and better tools, more and more data, and also higher and higher degrees of automation. And this research is about pushing this boundary even further in this direction, which is motivated by and needed due to current trends and challenges. And one big trend is that cyber attacks nowadays are getting more and more automated and scripted. And they're also evolving very quickly over time. So it's almost every day now that we see new vulnerabilities and new attacks being disclosed. And this not so nice trend, in combination with the trend that our infrastructures are also getting larger and more complicated, means that it becomes increasingly difficult to manage network security and to keep up. In response to these challenges, the goal of our research is automation and learning. In response to more and more automated cyber attacks, we want to automate more functionality on the security side. And in response to quickly evolving attack methods, we want to have security functions that are adaptive and that can co-evolve with a changing environment. To achieve this goal, we investigate self-learning systems. These are systems that collect data from their computing environment in real time, uses that data to make forecasts and predictions about the future, and then take actions based on those predictions in order to fulfill different security objectives. A concrete security function we have looked at automating using this approach is network intrusion prevention. So in this case, the self-learning system is observing its environment through a set of security indicators. And while observing this data process, the system needs to make an automated decision at every point in time, whether it should continue to monitor or stop and take a defensive action. And it also has to decide which defensive action to take. So this presentation will be about how can we automate that decision and how can we do that in an optimal way. So this is the outline. I started now with some motivation for this research and the use case that we are focusing on. Next, I will go into our approach for achieving this new level of automation and building this kind of systems on a very high level. And then we'll be more technical and go into some specific research results that we obtained, and both theoretical and numerical results. And finally, I will give an outlook on future work, what we are planning to do in this space, and my conclusions. On a very high level, our approach or method for automated network security functions can be understood through this picture that you see here. So the starting point is that we have a target system or a target infrastructure. And this corresponds to the infrastructure where we want to automate the security functions. Typically, this is a safety critical system or environment. And this is not an environment where we can easily run experiments and collect data. So what we do instead is that we take the configuration of this target system and we emulate that in our emulation environment. This then gives us a controlled and safe environment where we can run experiments, so we can run different types of attacks and different types of defenses, and we can measure and we can observe. And using these measurements, we then identify a system model. This system model then allows us to do theoretical analysis of the problem and also to apply numerical methods to compute optimal or near optimal defender strategies. We then take the computed defender strategies and we evaluate them in this emulation environment. We then have this conjecture that since this emulation system is a very close replica of the target environment, namely it has exactly the same configuration and exactly the same software as the target system, but runs on a different physical layer, a virtualized physical layer. Therefore, we conjecture that the performance of a strategy that runs in the emulation here will not be very different from the performance that we can expect when we implement that strategy also in the target system. So that is the high-level overview of our approach. And now I will go into each of these steps here in more detail. Starting with the step where we go from the target system to our emulation environment. So the target system in our case is the infrastructure that you see here to the right. So it's a very generic IT infrastructure, which consists of about 30 physical components, which are mixtures of application servers, gateways, and switches. And they're connected in this topology that you can see here. So we emulate each physical component of this target infrastructure using a Docker container. We emulate vulnerabilities and services and programs offered by these physical components using software that runs inside the containers. We achieve network isolation and resource constraints on these containers using standard modules in the kernel, for example, netdem and cgroups and namespaces. We emulate arrivals from the client population that you see on the top here, using a stationary Poisson process. So at every time step, we sample the number of new clients from this process, and then we spawn new containers corresponding to those clients. Finally, we emulate internal connections between nodes inside the infrastructure, so behind the gateway here, using gigabit connections with 0 packet loss, and we emulate external connections between the gateway and the attacker and the clients using 100 megabit connections with some packet loss. And these numbers are drawn from previous empirical studies on enterprise networks. So using this method here, we can take almost any target infrastructure, and we can then create a realistic emulation environment of that target system. And this emulation environment then allows us to have a safe environment where we can run different types of attacks and different types of defenses, and we can compare them, and we can measure, and we can observe the system. Using these measurements, we then identify a model of the system. And the way we model this kind of systems is as discrete time dynamical systems with Markovian dynamics and partial observability. So we assume that the system has some state. This state, however, is hidden from the defender. So the state summarizes all information about the system and its current execution. And this includes also information about the possible attack. So this information is generally not completely observable to the defender. The defender instead observes observations, which may be correlated with the state. For example, the defender can read log files, it can collect alerts, and it can read other metrics from the system, but it doesn't know exactly the state of the current of the system. These observations are then fed through a filter that computes a belief of the current state. So based on all of these metrics that we collect, the history of all of the metrics, we feed that into a program that computes a belief of the current state based on this history of observations. And this belief, which is formally a probability distribution over the state space, that is then fed into the controller, which will take an automated decision of the next defensive action to take. And this could also be to decide to not take any action at all. So this is a closed loop feedback system, and we typically run this loop and we implement it in practice in a frequency of about 15 seconds, which may sound like a pretty slow frequency, but in practice, the type of actions we want to take here generally does not make sense to take more frequently than that anyway. And in fact, if you run this loop at a very high frequency, you are very sensitive to noise and instability because it takes some time for the observations to propagate. And if you try to run this loop at a very high frequency, then you may take actions just based on noise. So we also looked at slight variations of this model. So in some of our work, we have assumed that the attacker is static or scripted, and then this becomes a partially observed Markov decision process. In other parts of our work, we have assumed that the attacker is dynamic, and then this becomes a partially observed stochastic game. Then taking this formal model, we can now instantiate that with different parameters depending on the system we're looking at. And we take those parameters based on the measurements from the emulation environment. So in general, we have very good information about the complete configuration of the target system, but something that we typically don't know is the dynamics of the system. So how does the system perform under varying conditions? That is under varying load, under varying attacks, most importantly. So we estimate this unknown information using data that we collect from the emulation environment. And here you can use basically any identification method or estimator. In our case, we found it to work very well with Gaussian mixture distributions based on the data that we collect. So for each of these security indicators and different metrics that we're recording, we fit a Gaussian mixture distribution as a conditional distribution over that metric given a current state of the system. And finally, given now that we have estimated this dynamics, and we have that then gives us a complete computational environment where we can simulate the system, and we can also apply numerical methods to compute optimal or near optimal defender strategies. And this we can do, for example, using reinforcement learning, using game theory or other optimization techniques like dynamic programming, for example. So that concludes the high-level overview of our approach and how we are going about building these kinds of self-learning systems. Now I will go into more technical details on our current research. But before I do that, I will give you a little bit of context of previous work in this space. And I'm going to classify the related work here in 2 dimensions. So on the y-axis, you have external validity. And this corresponds to what degree can we validate the claims in the paper on a realistic system. And on the x-axis, you have the complexity and sophistication of the model that they use and of the control and learning technologies that they apply on that model. So naturally, I will place the early work in this line of in this space down in the left corner here, where they focused on very, very simplistic use cases, not so advanced learning and control technologies, and basically had no validation at all on a realistic system. But still very important and fundamental research with presenting new ideas and open up for much future work in this space. Then if you follow this line of work from the early papers, you'll see that we're going in this direction here, where we have gotten a lot better at modeling complicated systems and designing sophisticated control and learning approaches and algorithms on top of those systems. But we're still quite far from something that could work in a realistic environment. You may say that we are maybe on some exponential curve here, and if we just continue a few years, maybe we'll be reaching the goal. But I think no one can argue, at least, that at this current moment, we are quite far from having a system that can automatically take decision for us in a security environment. So when we started looking at this line of work and we're working in this space, we decided to take a slightly different approach. And we started working from the top left corner here instead. So starting with a very simplistic model so that we can make sure that we can validate any claim that we make in our paper on a realistic environment. And then only when we understand that model properly, the simple model, then we start adding more complexity and making the model more realistic. And that's the kind of research trajectory that we are on currently, and I will try to summarize now in 5 or 6 minutes. So the first result we obtained, we assumed that the system or the defender is observing its environment through a set of security indicators, and that at every moment it can only decide between 2 different options. Either the system just waits and does nothing, or the system chooses to block all network traffic. And then we wanted to know, okay, given these very, very tough constraints on the defender, what is the optimal strategy? And how can we compute that strategy, and how can we implement that in a realistic system? So formally, this actually corresponds to a optimal stopping problem, where we want to find the optimal time to stop a certain stochastic process. And relating this back to the model that we had before, this is just a particular instantiation of this general model, where in this case, we have only 2 states, 0 and 1, where 0 means that there is no intrusion, 1 means that there is an intrusion. And here we define the observations to be alerts from an intrusion prevention system. And otherwise, the loop is the same. So the observations go through the filter, which computes a belief of the current state, so belief of intrusion. That belief goes into the automated stopping strategy, which then will decide when to wait and when to block the network traffic. Now, it turns out that we can say quite a lot about the optimal strategy here for the system from a theoretical perspective. So consider now the belief space of the defender. This is the belief that the defender has that there is an ongoing attack. where 0 means that you know that there's no ongoing attack, 1 means that you know that there is an attack, and everything in between we have uncertainty. Then we can show that there exists a threshold, so that the optimal thing for the defender to do is just simply to wait and do nothing until your belief reaches this thresholding point, and then you should block the network traffic. So whenever you enter this set here, then you should block the traffic. And it also is possible to show that this set here will always be convex. Even now we're just in 2 dimensions, but even if you have a higher dimensional state space, this will be convex. And of course, we don't know what this threshold is, but by the theory, we know that it should exist at least. But we have to compute it to find also the optimal strategy here for the defender. So this gives rise to a very, very simple optimal strategy where the system will just wait and wait and wait, updating the belief until we're reaching this thresholding point, and then it will switch and block the network traffic. So that strategy is a strategy that lends itself very well to both understanding from a theoretical perspective, and also to implement in a practical system. And that's exactly what we did. So due to an interest of time here, we're just going to focus on the leftmost column, and that shows the reward of the system. So we want to maximize the reward. And the performance of the system is shown both in the simulation and in the emulation, where the red curve shows the simulation results and the blue curve shows the emulation results. So what we can conclude from these results is that our approach can indeed very efficiently approximate the optimal strategy and compute this threshold. And secondly, we can also see that the performance, once we have learned this threshold, is very good, both in the simulation and in the emulation. That it will perform well in the simulation was kind of expected, and this is nothing new. It's been known for about 20 years that we can learn this kind of strategies in a simulation environment. But the fact that it also works very well in the emulation environment is new. And this is very encouraging to us. So even though this is a very simplistic model, this shows sort of the possibility of using this technology to automate various security functions. So that is our baseline result. And now we have since then we have been trying to generalize this result and make the model more realistic. And the first generalization we did was that we dropped this assumption that the defender only has 2 possibilities, either do nothing or block the network traffic. So now we assume instead that the defender has an arbitrary number of possible defensive actions that it can take. But we still have this constraint on the defender that it should take those actions in a specific order that we know a priori. So we should start with the least draconic action, and then increasing the severity of the defensive actions in order. And by having this constraint, the problem then formally becomes a multiple optimal stopping problem, which clearly is a more sophisticated, more general problem than the previous formulation. And this can easily be seen because now we have this free parameter L, which we can decide. And if you set this parameter L to be 1, which is the maximum number of actions of the defender, then we recover exactly the problem that we had in the previous paper. So then we can invoke that theorem, and we know that there exists an optimal strategy for the defender, which is defined by a single threshold here. Now it turns out that we can also generalize this theory so that this threshold optimality also applies in a more general sense, where if you have L different defensive actions, you will have L different thresholds that are decreasing in L, so that the optimal thing for the defender to do, or for the self-learning system to do, is to simply collect measurements, update the belief, and then if the belief is above a given threshold, then you take the corresponding action, and otherwise you just wait. And knowing that there exists an optimal defender strategy on this particular form, we can then very efficiently learn it and then compute it. And we have designed an algorithm for doing exactly that, which we show here the performance of in red. And we compare that to 3 different state-of-the-art algorithms. One state-of-the-art reinforcement learning algorithm, PPO, one state-of-the-art change detection algorithm, which is Shiryev's algorithm, and one state-of-the-art dynamic programming algorithm, which is heuristic search value iteration. And what we can notice is that all of these algorithms eventually reaches an optimal solution or very close to the optimal solution. But as can be shown here in the figures, our algorithm reaches the optimal solution much more efficiently, much quicker. And the 3 different figures here show the performance against 3 different types of attackers. And we see the similar trend on all 3 cases. The next extension we have done to our original model is that now we assume that the attacker can also be dynamic. So in the previous work, we have assumed that the attacker follows a static strategy, but now we assume that the attacker is also learning and is also updating his strategy over time. And most importantly, the attacker also knows what strategy the defender is following and may try to exploit that. So if you consider, for example, the defender strategy we had in the first paper, which was just a single thresholding strategy, obviously that is a strategy that could easily be exploited by an attacker by simply trying to make the defender block all the network traffic to achieve a denial of service attack. So now when we assume that the attacker is dynamic, we no longer have a decision problem, but we rather have a game theoretic problem. And that means that we want to find a Nash equilibrium of this game, or a max-min strategy of the defender, which gives the best possible strategy for the defender when facing the worst case attacker. And analyzing the problem theoretically, we cannot say as much theoretically, but we can say something at least. So the first thing we can notice that we don't know anything about the structure of the equilibrium strategies in this case, unfortunately. But what we can say is that we at least know the structure of the best response strategies, because if we fix the attacker's strategy, then this game actually reduces to exactly the same model that we had in the previous paper. And then we know that there exists an optimal strategy for the defender, which is of a thresholding type. And we can also extend this result to the attacker. So if you fix the defender's strategy, then there exists a threshold strategy of the attacker that is a best response. And knowing that there exist best response strategies on this particular form, we can then approximate an equilibrium of the game by iteratively computing these best response strategies and taking the average of these strategies. And this process is called Fixture's self-play. So we implemented exactly this algorithm in estimating these thresholds iteratively with an algorithm we call TFP. And we compare it here to two state-of-the-art algorithms. First, we compare it against Neural Fixture Self-Play, NFSP, which is a state-of-the-art reinforcement learning algorithm for approximating equilibria in this kind of games. And we also compare it against a state-of-the-art computational game theory algorithm, which is heuristic search value iteration. So what we can note is that our algorithm is much more efficient in reaching a good approximation of the equilibrium of the game if you compare it to the NFSP algorithm. However, if you compare it to the algorithm from computational game theory, HSVI, then the difference is the gain is not as big. It's still a little bit more efficient, but they're kind of similar in performance. The final extension we have done to our work is that we have considered also dynamic environments. In our previous work, we have assumed that while the attacker and the defender may update their strategy over time, we have assumed that the environment remains more or less stationary and doesn't change. The environment may be stochastic, but it doesn't change the dynamics over time. However, we know that in an operational environment, this assumption will not hold, since in an operational environment, we will always have failures will happen, upgrades will happen on a regular basis, and other types of reconfigurations. And we don't want that our system has to be updated and just break every time these changes happen. We want our system to be able to adapt to these changes. And to this end, we have extended our algorithm or our framework to adapt dynamically to changing environments. And this is not really a very sophisticated extension. It's quite intuitive. It just means that every time we are updating the policy of the defender or of the self-learning system, we are at the same time also relearning the model of the system in this loop. So we're putting basically model learning in the loop. And we have designed a very generic algorithm here for doing this kind of iterative model learning and policy learning. We did an experiment also where we applied this algorithm and ran it for 50 hours in our emulation testbed. And we instrumented the testbed then with a periodically changing dynamics following the sine curve here. And what we find is that this algorithm is able to track continuously very close to the optimal performance, which you see in pink here. And we can compare that to the performance that we had of the previous version of the algorithm of our framework, we should say, which is shown in green, which has a much more spiky performance. Now, one caveat here is that this algorithm we have currently only works if the changes in the target system is not too frequent. So here we assume that the system remains static for maybe 5 minutes so that we have time to adapt our algorithm. If the system changes more frequently than that, then we expect that our system will have problems to keep track of the changes. And this is something that we want to investigate further in future work. So what we're planning to do in the future, I think the first direction of future work you can already guess based on our current research trajectory, in that we want to close the gap to reality. So to keep extending our model to better capture realistic use cases and drop some of the assumptions that we have that are currently not realistic. The second direction for future work is that we also want to extend our solution framework. And this is quite exciting because there's a lot of room for extending our framework that we haven't really exploited yet. And one such extension is that in our current framework, we are constantly learning a model of the system, but we're not really exploiting that model for taking actions and for doing control. So in the future, we want to look into better exploiting that information by using rollout-based reinforcement learning techniques and also model predictive control. And the final extension is that we also want to extend our theoretical results. And this is actually tied to the first point here, because we know that as we will extend the use case and make it more complicated, then we quickly run into a problem of scale. And we have to be clever here to find the right balance and the right abstractions where we can capture complicated use cases, but still maintain some level of analytical and computational tractability. And we are betting very heavily that theory will guide us towards that balance. So in conclusion, in our work, we develop a framework for automating certain types of network security functions. We have applied that method to an intrusion prevention use case and developed a whole solution framework around that. And this framework rests on a very solid foundation with hard results obtained from a practical system. And following this approach, we've also been able to discover some interesting structure of optimal defender strategies in different conditions. So we know a little bit better now what it means to be optimal as a defender in different situations. So thank you very much for listening, and please drop me an email if you have any questions about this work. Thank you.